Today we're going to learn how to identify linear functions. So you have to be able to identify them from graphs, from equations, and from tables. So let's refresh on what a linear function is, or what a linear equation is. So a linear means it makes a line. So the points make a line. It has a constant, which means it has a slope. And we have to then see if it's linear and it's a function. So we have to remember what a function is as well. We know a function cannot be anything that repeats the x values. So if we had a graph, let's say, that looked like this, and we had a line graphed here, this would not be a function, because if we do the vertical line test, it would not qualify as a function because the x's repeat. So this would not be a linear function, even though it makes a line. So you got to be careful with that one. That was the only little difference. You got to make sure it's a linear function. All right, so let's look at the different types of graphs that you possibly could see. So the first one we're going to look at is linear. So maybe, and linear can go in any direction. It can have any kind of slope other than no slope. This is a no slope. We can't have that. But we can have a zero slope. So we could have one that goes like this. So we could have a line that goes like that. That would be a linear function because it passes the vertical line test. We could have one that goes like this. That's also a linear, and it's also a function, so it's a linear function. We could have one with a negative slope. We could have one that goes like this. So individually, those are linear functions on a graph. Other examples that you may see that are non-linear, and we'll talk about specifically what they are, you may see a shape like this. This is called a parabola. The shape is a parabola, and it's kind of spelled kind of like a parabola. A lot of people say that, but it's a parabola. This happens because of quadratics, because something in the formula or in the rule has a exponent of 2 or a squared. This is non-linear. This is not a linear function. It's still a function because it passes the vertical line test. If we check and we did our vertical line test, it passes that. It only hits one point at a time, so it's still a function, but it's a non-linear function. This one, the one we did before, passes the function test and it makes a straight line, so it is a linear function. Another one that you might see would be something like this. This is called an exponential. And it's still a function because if we use our vertical line test, even though that one kind of looks straight right there, it's not. It's little bitty pieces over and over. This is an exponential. It does pass the function test, but it's not linear. It's an exponential. You get this from when you have an exponent that is a variable, and we'll see more of that in the equations. The other type that you may get is something that looks almost like an exponential but doubled. It looks like this. This is called a rational function, and it is also non-linear. Okay, this one was non-linear as well. So these are all functions, but the only one that's linear are the ones that make a straight line and pass the functions test. So now let's talk about equations. What our equations would look like if it's linear versus non-linear. So I've got 4 equations here. We'll show the first 2 first. So the first one, y equals 3x plus 2. When we look at what's beside the x, we see a 3. This tells us is our rate of change. Our slope is 3. So this is in slope-intercept form that we're used to seeing, which is that y equals mx plus b that we've learned this year. So when we have an exponent of 1, so you think, well, where's the exponent of 1? Well, there's always an exponent of 1 if it's not shown. It's there. It's just invisible. We don't write it, just kind of like we don't write a 1 in front of just a variable if it's just 1x or 1y. We don't need to write the 1 in front of it. So anytime we have an exponent that just has a 1, or a variable that has a 1. We don't necessarily see it, but this is linear. So this is a linear equation. And this tells me that there's a constant or a slope, which tells me that it's linear. And we know how to find slope by looking and how to calculate. We don't necessarily see that exponent of 1, but the exponent on the x, so we'll put it on the x, is 1. And we don't always see it. Sometimes they just don't write it. Usually they don't write it. Okay, let's look at the next example. This one is 3x and the exponent is 2. Well, this we know is not an exponent of 1. So immediately we know it's nonlinear. We know it's not linear because it has an exponent bigger than 1. It's nonlinear. Specifically, because it has an exponent of 2, this is a quadratic. And remember, the quadratics, they make that little parabola or parabola, and they have that little curve. So on a graph, they make that little curve. Looks like a little U. And these U's can be like this or open up. Okay, and that's still a function, but it's not a linear function. It's a quadratic, and the exponent is 2. Okay, let's look at our next example. Notice the exponent for this one is x. So the exponent is x. Immediately, we know the exponent's not 1, and it's x, so this is nonlinear. This is called an exponential, which kind of makes sense. X at the top, exponential. And this is something that you'll learn in Math 1. The exponent is the variable x for our purposes. So we know it's nonlinear. It still would make a function. Remember, it makes a graph that kind of looks like that. It also can look like this. Okay, and we use these a lot when we're talking about cases that rise exponentially. So if you're thinking about like the flu spreading or coronavirus or something like that spreading, that would be considered exponential, kind of how it's grown. The last one, we notice that the x is in the denominator. So even though it has an exponent of 1, it's in the denominator. So it cannot be in the denominator, no matter what exponent it has. This is nonlinear. This is called a rational. And it makes that graph that kind of looks like that with the double sides. This is rational, and the exponent is in the denominator. So we can't have an exponent in the denominator. So when we look at the 4 that we've done, the only one that's linear is the one written in slope-intercept form. Now remember, we can have some that could be written in linear form, but they don't look in slope-intercept form. They may look like this. They may be like 3x plus 2y equals 6. This is still linear, and if we look at it, find our x, we found it, we look here, let's see if anything's there. There's nothing there, so that tells me there's actually a 1 there. This would be linear. All right, so now let's go to tables. So we're just going to talk about 3 different types of tables. You have to be able to distinguish which ones are linear and nonlinear, but I'm going to show you how you would know if you had to classify if something was something different besides linear. So the first thing we're going to do is we're going to use our strategy of going from one point to the next and seeing how do we get there. And we always think about adding or subtracting. So how do we get from 3 to 15? Well, we added 12. How do we get from 15 to 19? Now these are not in order for a reason, to show you that it can be all mixed up and you still need to look at your strategies. This we subtracted 6. 9 to 6 we subtracted 3. 6 to 27 we add 21. 27 to 39, we add 12. So you look at this and say, this is just a hot mess. It has no pattern. That's okay. We're going to keep going. Now we're going to look at the y's and we're going to look at their changes. How did 20 become 12? Well, we subtracted 8. How did 12 become 16? We added 4. 16 to 18, we added 2. 18 to 4, we subtracted 14. And 4 to negative 4, we subtracted 8. Now, to see if it's linear, it has to have a constant or a rate of change or a slope. So we're going to take a change of y, remember it's change of y over change of x, and we can take any two that we want. So we want to check. So we can have here and here. So a change of y, so negative 8 over 12, and that simplifies down to negative 2/3. Well, that's great. Let's check another spot. Let's do here. We have the change of y's is 2, and the change in x's over negative 3. Well, those are the same. Notice those are the same. So far, it's consistent. Let's do one more check. We'll do the bottom one, comparison. So negative 8, again, over 12 is going to give us what we had before here. Same thing. We can check another one that's not the same. Negative 14 over 21. Negative 14 over 21. We can simplify that down again to negative 2/3. So these are all constants. So this has a slope. This has a constant, a rate of change. So we know that this is linear, and it has a slope of negative 2/3, and it's constant. Now let's look at our second example. We're going to do the same strategy every time we see table or a list of coordinate pairs. We can put them in a table. So 0 to 1, we know we did 1. 1 to 2, add 1. 2 to 3, add 1. 3 to 4, add 1. 4 to 5, add 1. Well, this has a beautiful pattern. That does not mean that it's linear, so we have to keep going. On to the y side. 5 to 7 plus 2. 7 to 13, we go plus 6. 13 to 23, we did plus 10. Then 23 to 37 plus 14. And 37 to 55 plus 18. Now notice we had a constant over here and a constant, our changes over here. We're going to check and see if it's linear. We're going 2 over 1. Well, 2 over 1 gives us 2. Let's check another spot. Let's do 10 over 1. Well, I know immediately that 10 over 1 is not going to simplify to 2. It's going to be 10. These are not the same. So immediately I know it's not linear. This is non-linear. If I go further and I want to see if there does become a pattern, I can actually look and go further and say, okay, well, is there a pattern if I do this again? So 2 to 6, I get plus 4. 6 to 10, I get plus 4. And so on. I do see a pattern. This first time we did it is called the first difference. The second time is called the second difference. So if there's a pattern that's constant on the second time we check the y changes, this is actually a quadratic. So that's a little dip into the future, but we know immediately because it doesn't have a slope that it is not linear. Now let's look at this last one. So again, we're going to look at our changes from here to here, here to here, all the way down on each side. So we have plus 1, plus 1, plus 1, plus 1, plus 1. Then we're going to look here. 5 plus what got us 11? Well, plus 6. 11 to 29 is plus 18, plus 54, plus 162, and then plus 486. Well, immediately if I look and say, okay, my change of y over a change of x that's right connected, 6 over 1, great. That means every one of these should simplify down to 6. Well, 18 divided by 1 is not going to be 6. So immediately we know this is non-linear. If we go further and go into our second difference, we see 6 to 18, that would be plus 12. And then 18 to 54 will be plus 36. Again, There's not a constant pattern like there was in this one with the second difference. When there's not a constant pattern, we have to look further and see if there is something that we multiply by to get to the next number. And this one is a multiple. We won't go into all how to do that, but this one is actually exponential. And again, that is something you'll learn in Math 1. All right, so now let's look at some examples. So this one might be a problem that you might encounter. So it says, which table of values represents a linear function? So again, we're going to use our strategies, 0 to 3, 3 to 6, 6 to 8, and we're going to look at the rate of change for each one. Well, 0 to 3, I add 3 to get there. 3 to 6, add 3. 6 to 8, I add 2. That's okay. All right, from -4 to get to -3, I'm going to add 1. Think about our number line. If we're at -4 and I want to go to -3, I'm going right one spot. So I'm adding 1. Same thing I can think about, -4 plus 1 gets me -3. Then I add 1 and I add 1. Now let's check see if there is a slope. Well, this is a change of 1 over 3. This is 1 over 3. So those are identical, but this is 1 over 2. It cannot all of a sudden change. This is nonlinear, so this one will not work. So let's look at another one. 6 to -2. If I'm at -6 and I go to -2, I'm adding 4. If I'm at -2 and I go to 3, I'm adding 5. And 3 to 8, I'm adding 5. We'll check our y's. 8 to 6, subtract 2. 6 to 4, subtract 2. 4 to 2, subtract 2. Check and see if my slope is constant. Change of y, -2 over 4, would give me -2 over 4, would actually give me a -1/2. And then if I notice next, it's -2 over 5. It's not going to be linear. It can't all of a sudden change its direction. That is not linear. It would make a graph that kind of starts straight and then kind of does a little boop and a little takes off, or a little dip. So this is not linear. So this one will not work. So let's look at C. So we have 2 to 3, so that's +1. 3 to 5, +2. 5 to 7, +2. 5 to -3, we're going to go from, remember, if we're going from much bigger negatives to smaller negatives, we're actually adding. So add 2. 3 to -1, add 2. And 1 to 1, we add 2. If we notice immediately, 2 over 1, all of them should be 2 over 1, but this is 2 over 2, which simplifies down to a whole, to 1. So this also is not linear. Let's look at our last one. 3 to 5, +2. 5 to 7, +2. 7 to 9, +2. Then -4 to 0, +4. 0 to 4, +4. And 4 to 8, +4. Notice with these, this is 4 over 2, 4 over 2, 4 over 2. That's constant. That's the same every time. This one is our linear function. It will make a line when we graph it. You can always graph it on some graph paper and also see and connect those dots and see that it's a line. Sometimes you'll be given them in ordered pairs. You're going to do the same exact thing. And if it's easier for you to put it in a table, absolutely put it in a table. You can turn them and do it in a table just as quick. So X's and Y's, and you can just write your points: -4, 0, -2, 2, 0, 4, and 2, 6. And then check the same way we did the tables. So just because they're written long ways doesn't mean that you can't find them as linear functions. All right, so let's talk about if we are given a table and they need us to find the rule. So find what is the equation. So we learned long ago this year how to find slope. And so we're going to put this in, we're going to make an equation for this table and slope-intercept form. So y equals mx plus b form. Remember, our b is our y-intercept. It's where, if we were to graph it, it would hit the y-axis. And it's always where x is 0. Sometimes the table tells us exactly what it is, sometimes not. Our m is our slope, or our rate of change, or what we found our constant was. And then our y and x are individual points on the table. So first we need to see what we know about the slope. So the first thing we're going to do is find the slope. So 0 to 1, we add 1. 1 to 2, we add 1. 2 to 3, we add 1. And 3 to 4, we add 1. Now let's go from -1 to 4. Well, -1 to 4, we add 5. 4 to 9, we add 5. 9 to 14, add 5. And 14 to 19, we add 5. So remember, rate of change is change of y's over change of x's. So our change in y's were 5, and it was the same all the way through. So we know this is linear. It's telling us it's linear. Told us that in the problem. So we have 5 over the change in our x's are 1. So 5 over 1 means our slope is 5. So that means our m is 5. So far what we know is y equals 5x plus b. Now we need to find this b. Well, b is always when we look at a graph, it's anywhere that graph, when we draw it, hits the y-axis. And it could be anywhere, but it's where it hits the y-axis. So it's always when x is 0. So let's look at our table. We have an x here and we have a 0. So where x is 0 is our y-intercept. Well, it's -1. So this b we're going to replace with a -1. So this would be the function or the rule, the equation for this table of values. Now that's a pretty easy level because the table gives you the y-intercept. So let's go to one we don't know the y-intercept by looking at the table. We're still going to start with finding the slope, okay? And if we know the table's already linear, because the problem tells us it's linear, we're not trying to prove that it's linear. We know it's linear. So we're going to find the slope. So first step, find slope. And we're going to do that by looking for the pattern. So 1 to 2, 2 to 3, 3 to 4. We do that by +1 each time. -1 to -6. So this, think about your number line. You're at -1 and you're going to -6. You're going this direction. So you're actually subtracting more. So I'm subtracting 5 from -1 and a -5 get me a -6. And then -6 to -11, I'm subtracting 5. -11, -16, I'm subtracting 5. So then we find our slope. Remember, slope is change of y's over change of x's. For us, it's -5 over 1. So -5 over 1. So we know our slope is -5. So we're going to go ahead and plug that in. So the second step, plug in your slope. So plug in your slope to y equals mx plus b form. So we're going to do that. So y equals -5x plus b. The next thing we're going to do is we've got to find the y-intercept. And if we look at our table, we say, uh-oh, we don't know when x is 0. We don't know. We know it would be right here somewhere, but we don't know what y would be. Now this one's pretty easy to kind of count backwards. We know that this went up by 1, so if we went back, we have one more spot there, we know going back would be 0. So from 0 to 1 is 1. So that keeps that same pattern. We would have to then go back the same amount to match it. So if we go back here and we think about what would be adding 5, so going back even more, we could also find it that way. Now, sometimes that can get confusing with negatives and positives. We make little mistakes with our integer rules, but we can also we know we're looking for what y is when x is 0. So let's plug in a value of what that would be using any point on the table. So let's say we just use 1 and -1. This is an x value and this is a y value that's supposed to work for our equation that we're making. So we're going to substitute those in for our values. So when x is 1, we still don't know our b, we know that y should be -1. So now we can solve for our b. -5 times 1 is -5 plus b was -1. We're going to move over and we end up with 4 equals b. So think about if we went back, just like we did here, we added 5, it's like going back here, we would know that this would be 4. So now that we know our y-intercept, when x is 0, y is 4, we're going to rewrite our final answer. So y equals -5x plus 4. This would be your final answer. All right, let's look at one more that's not as clear. So the first thing we do, we find our slope. So we look for our patterns. So a -3 to 2, we've added 5. 2 to 7, add 5. 7 to 12, add 5. Fantastic. 7 to -2, we're going to add 5. 2 to 3, add 5. And 3 to 8, add 5. Okay, so we see our change of y, 5 over 5. So 5 over 5 is actually just 1. So that means our slope is 1. So we're going to plug that into y equals mx plus b. For our m, we now know that it's 1. And I'm going to use the 1 here so we don't forget that we've done it. Now I need to find the b. So instead of counting backwards, which I can't do as easily on this one because 0 would be somewhere in between here, it'd be kind of splitting the difference. I'd have to kind of figure out how much of a difference, and that's a little bit too much work. We want to work smarter, not harder. So I'm just going to pick any 2 points on this graph. So I think I'm going to pick 2 and -2. So when x is 2, so let's rewrite what we have here. So when x is 2, so I'm going to plug him in, y has to be -2. So now I'm just going to solve. 1 times 2 is 2, plus b, and then minus 2 to move it to the other side, minus 2. This side cancels out. -2 and -2 gives me a -4 is now my b. So now I know my b and I know my slope. Now I can write it as y equals mx plus b. So I have 1x minus 4. And then I can double check any point here and actually make sure it works. So like if I put 7 and 3, 7 times 1 is 7 minus 4 would give me 3, and it works.